We then have moved to here in 2019, and this is the second meeting here, and we didn't have a live face-to-face meeting last year. We had a Zoom meeting, in which many people on the screen now participated. So, should I say something about this building?
If you wish.
Yeah, this is a very interesting building because it was built by a Confederate person who lived in England. He had it built, and he had it built in this Georgian style in about 1863. And when it was a relatively new building, this is where the Confederate surrender in the naval part of the American Civil War was signed.
This was the Confederate embassy,
That was the
United States.
Because this man was the Confederate, right? So this was the Confederate embassy here. So then 1865, and then when the Civil War was over, sometime afterwards, Jefferson Davis came and lived in this building, the Confederate president. Just behind the park there is the place where John Lennon was born, which is which was a maternity hospital. So this was the education library, but this is now part of architecture department. It's next to the physics department, which is just that way, if you can see me. That way. Okay, well I think we should start, and our first speaker is Dennis Morris, and why our fourth-dimensional space-time is four-dimensional and the Fermion content of the universe. Right. Over to you, Dennis. I'll give you a bit of extra.
Thank you very much for inviting me. What I'm going to show you is a little bit of research that started about 20 years ago. I was going to write a small booklet about doing complex numbers using matrices. It was only intended to be it was just doodling with mathematics. It led me down paths I could not have imagined. I'm in a situation now where I've got a completely different understanding of the nature of mathematics, of the nature of algebra, and what seems to be the foundation of the unified field theory has just fallen out. I understand why the universe is four-dimensional. I understand why we have the Fermion content and the forces that we have in the universe. What I've got so far has not been tested against observation, and it's not yet been quantized. For the last 3 years I've been a little bit stuck, not knowing what direction to take it in. But I will offer you an explanation of why the universe is four-dimensional, and I will offer you an explanation of why we have the forces that we have, and I will unify them in a mathematically unified way. This is not going to be a unified field theory where all the different forces are different aspects of one force. This is a mathematically unified expression of all the different forces that come out of it. What's basically going to happen is very similar to gauge theory, but instead of doing gauge theory with Lie groups, I'm going to do them with finite groups. Within gauge theory, there is the idea that an electron has its own internal symmetry space. And it says no more than an internal symmetry space, there's a little more about it. What I'm going to say, it actually has a space with a rotation matrix, with a distance function and all this. It's quaternion space, in fact. These spaces are going to act like potentials that float and vary locally over four-dimensional space-time. And instead of doing gauge theory by differentiating a Lagrangian, we're just going to take these as a potential that varies over space-time. We're going to differentiate the potentials to get the fields. We're going to differentiate the fields to get the equations of motion. We're going to use non-commutative differentiation to differentiate the non-commutative potentials. If you've got a non-commutative field, the differential dy over dx is both dy multiplied by 1 over dx and 1 over dx multiplied by dy. So you actually get two differentials out of a non-commutative potential. Those two differentials become two fields: electric, magnetic, electron, neutrino. It turns out quark neutrinos. Quark neutrinos have never been observed yet, and gravity and gravitomagnetic. that the gravito-magnetic fields all cancel, leaving a zero gravito-magnetic field, but it leaves behind it magnetic energy. If that energy gravitates, it would be something like dark matter. We'll also do an explanation of the mass problem, the neutrino mass problem with its oscillations. That comes out as well. So, to begin, I want to get over the idea that rotation is associated with a force. If we accelerate a particle, it changes the velocity. It's associated with an acceleration, but it's also a rotation in two-dimensional space-time. That's what change of velocity is. So when you get a force, it's associated with a rotation. This is gauge theory. Get the idea that all forces are associated with rotation in an internal symmetry space, but we're going to do it with finite groups, not Lie groups. There are two types of rotation in our four-dimensional space-time. You might have thought, if you'd have come to this as a baby, that four-dimensional space-time would have a four-dimensional rotation. It doesn't. It has two-dimensional rotations, and two types of them in one space. We have rotation in two-dimensional space-time, which is change of velocity, and we have rotation in our normal Euclidean sense. We just rotate round. Magnetic field in classical electromagnetism is associated with Euclidean rotation, it goes round. The electric field is associated with accelerating particles, it's rotation in two-dimensional space-time. So we have two types of rotation and they match the two types of fields that we get. Right, I'm going to talk a little bit about the concept of Rn, of space being four one-dimensional spaces. We have this concept of R4. It is four one-dimensional spaces, but there's no angles in it. Each one-dimensional space does not have an angle. There's no orthogonality in it. There's nothing holding them at right angles to each other. There's no chewing gum or anything to stick them together. We have other concepts that have been given us by mathematicians, like complex spaces, where we have our axes are complex numbers, or even where the axes are quaternion numbers. And they too have no concept of angle between the axes and no concept of orthogonality between the axes. The concept of Rn as a space is, to my mind, utterly useless. And I'm going to give you something far better. What this research led me to is to rejecting the axiomatic system of mathematics. Within the axiomatic system of mathematics, you can make up any axiom you want. Basically, it's becoming a fairy story. You make up whatever you want and you put it in. It's only got to be consistent. Well, I'm rejecting all of that, and what I'm going to say is that mathematics is that which you find within the real numbers. You start from nothing more than the real numbers. You poke around inside the real numbers, and what you find, that's mathematics. It turns out that there's a unique four-dimensional space-time inside the real numbers. There's only one of them. There's no 5 or 6 or 7-dimensional ones. And there's all these different gauge spaces that come by virtue of the finite groups. The finite groups are inside the real numbers. So all I'm doing grows out of the real numbers. It's already in there. That's what so I'm rejecting the axiomatic system. Rejecting the idea. Also, rejecting the axioms, the axiomatic system. I'm rejecting some of the axioms of an algebraic field. According to axiomatic mathematics, an algebraic field has 14 axioms. These include the existence of an additive identity, the number 0, and the existence of additive inverses, negative real numbers. If you don't insist on those two axioms, you can find an infinite number of other algebraic structures of different types of complex numbers. 3-dimensional complex numbers, 5, 7, 97, there's an infinite number of them. And these actually form your gauge spaces. Just like the complex plane, complex numbers are associated with a space, that's a gauge space. The quaternion numbers associated with a space, that's a gauge space. Or potential space if you prefer. Within the real numbers we have order. We also have identity. 2 is not the same as 3, 3 is not the same as 4, and so we can permute these different numbers, 2, 3, 4, 4, 3, 5. and we get sets of permutations. We're doing observational mathematics now. We observe that our sets of permutations contain an identity, that they are closed, that each permutation has an inverse, and that they are combined together linearly or associatively, if you prefer. These are normally the axioms of a finite group, but we observe these properties within the real numbers. So we're now doing observational mathematics. I'm going to change the notation. This is how I started out. I'm going to write a complex number as A, is this matrix here, the A's and the B's with a minus sign there. As you can see, all the multiplicative relations are just matrix multiplication. It's a new form of notation. That change of notation and nothing more than that led me to what I'm presenting today. Just that minor change of notation. It turns out that what that says is that the complex numbers are permutations. We're going to write our permutations as matrices. A permutation matrix is a matrix that's got a single one in every row and a single one in every column and zeros everywhere else. These are all permutation matrices. There are also signed permutation matrices. The signed permutation matrices are either a 1 or a minus 1 in every row and a single minus 1 or plus 1 in every column. That is a representation of C2, the finite group, cyclic group of order 2. This is a representation of the cyclic group of order 3, and this is a two-dimensional representation of the cyclic group order 4. That's going to be the complex numbers. We're not going to get the complex numbers out of a monic minimum polynomial, x squared plus 1 equals 0. We've dispensed with that. We're going to get them out of the finite group C4. We've got the exponential is within the real numbers. And what we're going to do to get all our gauge spaces, we're just going to split the exponential series. If we split the exponential series two ways, where we pick every second term, we get the cosh function and the shine function. The cosh function and the shine function are the basis of two-dimensional space-time. If we put some minus signs in with them, we get the sine function. We're going to do it. We're going to take permutations of the terms of the exponential series. So instead of just permuting them using the group C2, which gives the cosh and the shine, or C4, two-dimensional representation of C4, which gives the cos and the sine, complex. We're going to also permute them using the finite group C3, finite group C4, the dihedral group D3, D4, and every other finite group that there is. So we're just picking out terms of the exponential series. What we find is these terms all hang together. They all become trigonometric functions in different spaces. So the spaces we're going to get are going to have a rotation matrix with trigonometric functions in it. There we go. Now, they also fetch with them a distance function. We just take the determinants of the matrix form that we got from the permutation matrix, and that gives us the distance function. The distance function is held invariant by the rotation matrix. So you've got a rotation matrix, you've got trig functions, you've got a distance function, they all fit together, they're all part of the same thing. What you sometimes find in mathematics is things like metric spaces, where they invent a distance function and then they decide they're going to put an inner product on it and they're going to make this inner product equal to the cosine. The cosine is associated with distance squared equals x squared plus y squared. It is not associated with any other distance function. So you can't put inner products on stuff that, or cosine as an inner product on something as a distance function other than x squared plus y squared. Frobenius and Dedekind did a little bit of this. We're going to take it a lot further than they took it. So what we're basically doing, we're picking terms out of the exponential series to form spaces, to form trigonometric functions. I've also got a concept of space now, which is a reasonable concept. A space should have angles, it should have distance, you should be able to rotate in it. If you can't rotate in it, it's not space. That's what I'm saying basically. So for example, Lie groups do not have anything to do with spaces because you can't rotate in them. I know there's some fiddled little bit of fudging that they try to pretend they can, but they can't. So a space is a rotation matrix, a distance function, and the trig functions that go with it. There was a philosophical question as to whether that amount of mass actually makes a space, or whether we have to import into that within our own heads the concept of length, but that's interesting for philosophical discussion, but we'll not dwell on that. There we go. Right, what we've seen is we've seen a kind of space emerge from the real number. We saw two-dimensional space-time emerge from within the real numbers because the cosh function and the shine function are within the real numbers because they're inside the exponential. We do another one. This is the finite group C4, two-dimensional representation. What we take each permutation matrix, we multiply it by a real number, and we add them. You don't need to add them, but adding them is a very, very convenient way of doing it. It would work if you didn't add them. When you add them, you get a complex number. The exponential of complex number gives the polar form of the complex number. This is the two-dimensional complex plane. We've got what I will call two-dimensional Euclidean space. Spaces are falling out of the exponential series and the finite groups. We know there's only two possible kinds of two-dimensional spaces because there are no other representations of finite groups with two dimensions. When we do this, we find there are no spaces of a Riemannian nature other than the two-dimensional ones, the complex plane and two-dimensional space-time, and the quaternion ones, 2 and 4. There's no Riemann spaces of 5 dimension or 6 or 11 or 12. So if anybody's setting string theory in 11 and 12 dimensional Riemann or pseudo-Riemann spaces, I'm sorry, the spaces are not there. Now let's look at the complex plane. In 1990, the mathematician Michael Atiyah said that we've known about the complex number I for 300 years now. It'll probably be another 300 before we understand it. Well, in fact, it's been about 30. We normally think of I as the square root of -1, but what I really is a permutation. And we see here that what multiplication is, it's a sequential combination of permutations. So we've got a different concept of what I is. You know, negative real numbers never did have square roots. People knew that 500 years ago. It's a permutation. And we've got two algebraic operations. One is adding different amounts, or adding amounts of the same permutation, and the other, multiplication, is the sequential combination of permutations. So when you multiply two complex numbers together, you're actually sequentially combining two permutations. We've actually done a complex multiplication here using nothing but permutations. The fact you can do it with permutations shows that's what they are. I'm not advocating this for 1 minute, but we see that by just sequentially combining permutations, we get the same answers as we would get with normal complex multiplication. The algebraic operation of multiplication is really the sequential combination of permutations. Some permutations are non-commutative. There are different types of non-commutativity. In the 8-dimensional representation of the quaternion group, there are no minus signs in that representation. We have BC equals D and CB equals E. That's different from the 4-dimensional representation where BC equals D and CB equals minus D. This is the quaternions IJ equals K and JI equals minus K. Because multiplication is a sequential combination of permutations, what we've actually got is we've got two permutations in, one permutation out. However, there's this thing, commutator. We multiply these two permutations together, we subtract those permutations, and we get another permutation out. The commutator is widely used within particle physics for no reason other than it works. Some bloke invented it sometime and it works, so we'll use it. It's never been properly theoretically justified. Well, this is a theoretical justification. The commutator is a bona fide algebraic operation. And we also have the anti-commutator. Now, the commutator and the anti-commutator are algebraic operations of a multiplicative nature. Differentiation is of a multiplicative nature. It's dy times 1 over dx. So we can actually differentiate and get a commutator differential and an anti-commutator differential, and it's all bona fide because they're all legitimate algebraic operations. The commutator and anti-commutator actually formed as a superposition of two products, and you don't actually have to do that, it's just a nice convenient way of doing it. Right, I'm now going to show you a three-dimensional space that you've never seen before in your life. It's nothing like anything you've ever seen. It's certainly nothing like you think it is. We're going to start with the finite group C3. It's represented by these permutation matrices. So we're going to permute the terms of the exponential series by picking out every third one instead of every second one. That's all we're doing. We're going to multiply them by real numbers, and that is our algebraic matrix form. That's what we're going to take the exponential of. When we get it, we get the commutative part forms that, and there we have every third term of the exponential series. 1b, b squared, and down at the bottom we've got it starting with c cubed here, 1 here, but c squared and c here. The b and the c have changed position. So it's just every third term of the exponential series. These are almost, not quite, trigonometric functions. We're going to call these things, this is my notation, you won't find this anywhere. That's just the names of the functions. So what we actually have when we take the exponential of this finite group C3 and we're picking out the third terms of the exponential series, we're actually getting this. And when we combine them together, multiply the two matrices together, we get this one matrix. That's a rotation matrix. These I've called the new functions. One of the amazing things about these is that you multiply something as complicated, multiply something as complicated as these together using a complicated matrix multiplication, and you get, look, you get these, I'll show you these next slide. That is a three-dimensional rotation matrix. It took me 18 months to convince myself of it. When I first met these functions, I was so utterly shocked by the nature of them that I literally fell off my chair, and for 6 weeks I called them fall off your chair functions. Then, wanting another name for them, and anticipating that nobody had ever seen them before, I called them new functions. That's where the name comes from. Right, one of the things I want to point out about this is this three-dimensional rotation matrix has two real variables for its angles. Two-dimensional angles have one real variable, three-dimensional angles have two real variables, four-dimensional angles have three real variables, 97-dimensional angles have 97-dimensional variables. No, 96 real variables. That is the nature of a three-dimensional angle. It's something you'll never see, it won't ever be manifest in our space-time. Again, the determinant forms the distance function. It's a cubic distance function. That distance function is held invariant by that rotation matrix, and that's done by the way that these functions vary with respect to each other as you rotate. And there we have them. There's the initial single variable functions. You multiply that lot together in a matrix using complicated matrix multiplication, and you get exactly the same stuff out, except it's two variables. The functions match completely. These are your three-dimensional trig functions, and if you reduce one of these variables to 0, you get this. So it's got to be that way, really. This is three-dimensional rotation. It is nothing like two-dimensional rotation. They're not quite just simple splittings of the exponential series. The splittings combined together in two variables. Are these spaces of an algebraic nature? There's no additive identity on the time axis. If you think of two-dimensional space-time, the two-dimensional space-time, the cosh function never gets less than 1. So we don't have an additive identity on the time axis. And there are no additive inverses, there's no minus numbers on the time axis of the two-dimensional space-time. So I'm chucking those axioms in the bin, I'm chucking the whole axiomatic system in the bin. Other than that, they have all the algebraic properties you could ever want. And that's because multiplication is sequential combination of permutations. And these are based on permutations. And these spaces come out of the exponential function, they are an infinite number of different algebraic spaces, every one with a rotation matrix, every one with a distance function held invariant by that. So now you can see that if we decide to do a bit of gauge theory and we say an electron has got an internal symmetry space, we chuck the internal symmetry space away and we get one of these spaces. And we know what rotation is. In gauge theory they talk about change of phase from one point to another in space-time. They say phase because they don't say angle because they've no idea what it is. We've got the angles. We can do gauge theory, the properly structured algebraic rotations without any... We've got none of the problems of gauge theory done with Lie groups. Here's another example, the left chiral quaternions. Turns out quaternions are come in two varieties, left-handed and right-handed. The handedness is in the commutation relations. Hamilton knew about this, and seemingly they've been forgotten because nobody else seemed to know about them until I rediscovered it. But they do come in two varieties, left-handed and right-handed. What we've done exactly the same. We've taken the four-dimensional representation. There's two four-dimensional representations of the order 8 quaternion group. One of them gives the right-hand quaternions, the other gives the left-hand quaternions. We've taken the four permutation matrices, just ones, multiplied them by a real number, and put them all together, and we've got our quaternion. In the same way that the complex numbers emerged from the group C4, these are emerging from the quaternion group. We're going to take the exponential of that to get the quaternion rotation matrix, and that's the quaternion rotation matrix, and that I believe is electron spin. It's got sines and cosines, but it's not quite the same as the sines and cosines, because the actual trigonometric function includes this c over lambda and this d over lambda. If you try to draw graphs of these, you'll find they're a bit like a particle, because as the numbers underneath in the denominator increase, the amplitude gets less, and so they're actually like a wave particle in themselves. I'm pretty convinced that's electron spin. There's twice as much spin in it as you would expect. That's one spin matrix, that's another spin matrix. That's two-dimensional Euclidean rotation. That's another two-dimensional Euclidean matrix. It's got twice the spin it should have. And what seems to happen...
Is that cosine and sine or quotient sinh?
Sorry?
Is that cosine and sine or quotient sinh in your previous?
That's cosine and sine. Sorry? Is that what you meant?
Well,
Previous slide.
Oh, previous slide.
Non-hyperbolic.
Yeah, they're just cosine and sine.
Just cosines and sine.
all right, okay.
We will actually be coming across some of those when we come to a four-dimensional space-time. What are we doing?
You missed a slide. That's it.
There we go. Right, we can make observations in our four-dimensional space-time. The idea is that when we make those observations, we can observe only two-dimensional rotations, because our four-dimensional space-time has only two-dimensional rotations in it. So we throw a four-dimensional rotation at a Stern-Gerlach machine, and it seems to collapse into a two-dimensional rotation as we observe it. And it could collapse either that way or that way, which is either spin up or spin down. And which way it collapses is probably driven by a hidden variable. It's hidden within the quaternion space, but that's non-local to us, so it's not got a problem with Bell's theorem. And so we'll never know what that is, because we've no mechanistic connection between quaternion space and our space-time. It'll collapse probabilistically. If you send it through a differently oriented Stern-Gerlach machine, it'll forget which way it collapsed, because it's really a four-dimensional rotation. And so what we get from a Stern-Gerlach machine is exactly what we'd expect. The chirality of the quaternions is in the commutation relations. Here we have the left-hand ones, ij equals k, these are what are normally called the quaternions. The right-hand ones, ij equals minus k. The signs are just reversed. So that's the difference between the left and the right-handed quaternions. We actually form superpositions of these eventually. Now we're going to come on to our four-dimensional space-time. We can derive all kinds of rotations that there are by taking, picking out permuting terms of the exponential series. When we do that, we look at all the four-dimensional ones, and our four-dimensional space-time is not one of them. I think there's about 24 different four-dimensional ones from the group C4, and four-dimensional representations of other groups and things. But anyway, it's not hard to do, you just do it, and our four-dimensional space-time is not one of them. The distance function of our four-dimensional space-time is well known, of course. We can fit 3 two-dimensional Euclidean rotations into this space-time because we can set 2 of the variables to 0, and we get a distance function that is respected by a two-dimensional Euclidean rotation. The rotation, the distance function fit together, rotation holds together, that holds invariant that distance function. So we can fit 3 two-dimensional rotations in. We can also fit 3 two-dimensional space-time rotations in. That's acceleration in 3 different directions. We have 2 copies of we have 2 types of two-dimensional spaces in our space-time. This is the complex plane for the hyperbolic complex numbers. It's the same as the complex plane for two-dimensional Euclidean numbers, but it's a hyperbolic form. It fills that part there. There's no negatives back here. There's no 0 on the real axis. That basically is the expanding universe. If you've got a space-time, as we have, 4-dimensional space-time that's got 3 copies of two-dimensional space-time in it, and two-dimensional space-time spatially expands as time increases, you're going to have an expanding universe. And that's what we've got. It's also spatially finite. This is the observable horizon. This two-dimensional space-time is not spatially infinite, it's limited by the observable horizon. However, we have 2 types of two-dimensional space in our space-time. The other one, the complex plane, is spatially infinite. So our universe has 2 types of infinity in it. It's spatially restricted by the observable universe, and it's spatially infinite as well. This is not a surprise. If you've got a telescope and you looked out to the edge of the observable universe, you'd see some galaxies and things. If you put that telescope on a rocket and accelerate to half the speed of light, you'll effectively rotate the axis of the hyperbolic complex plane, and you'd see more galaxies. They have to be out there, they have to be the same. And that's what we would see. So if you want to know whether the universe is infinite or not, it's both. Now we're coming to our 4-dimensional space-time. What time is it? How many? Oh, plenty of time.
11:33.
We've got quite a bit of time. Right, we're going to work with the order 8 dihedral group, the 4-dimensional representations of the order 8 dihedral group. And that's them. These again are just sets of permutations. The matrices with 1s and -1s in each column and noughts everywhere else. The numbers are my own notation. It means symmetric, symmetric, anti-symmetric in alphabetical order. The B's are symmetric, the C's are symmetric, but the D's are anti-symmetric. In each one of these we've got 1 variable that's anti-symmetric and 2 variables that are symmetric. Here we have the anti-symmetric one is in the B's, the symmetric one's the C's and the D's. They come in 2 varieties, left-handed and right-handed. These 3 are all left-handed. That's in the commutation relations. These are all right-handed. These numbers are known as split quaternions. They were discovered by James Cockle in 1848. James Cockle was president of the London Mathematical Society from 1886 to 1888. He also discovered the 2-dimensional hyperbolic complex numbers, 2-dimensional space-time. And he must have come within a whisker of getting special relativity back in 1848, but he didn't. Where are we going from here? Right, we've got to form the superposition of these spaces. We've got 6 spaces here and we're just going to add them together. We're going to just let them sit on top of each other. So what's the distance function that comes out of this? Well, if you travel through 6 spaces, you're going to travel through 6 different amounts. You're going to add up all those spaces, the sum of all those spaces. Well, we're going to do it in 2 sets of 3. 3 the left-handed distance functions and the right-handed. The left-handed distance function, these representations of that, it's the same as our 4-dimensional space-time, except we've got 2 minuses and 2 pluses. When we add them together, we get this, 3 minuses. Right-hand distance function is the same. We add them together, we get 3 minuses. The 3's and the 2's just get lost in the units, and we're left with, that is the superposition distance function of the order 8 dihedral group, the 4-dimensional representation of the order 8 dihedral group. It's a superposition space. It's not one of the gauge spaces that we form by just picking out terms of the exponential series. It's been formed by adding together such spaces as come out of the exponential series. It turns out it's unique. We have a left-handed one and a right-handed one. That's unique apart from the fact we've got 2 of them. So it seems that we're standing here now in a superposition of a left-handed 4-dimensional space-time and a right-handed 4-dimensional space-time. I have a right hand, I have a left hand. I cannot change this into this by rotation and translation alone. It seems they're in 2 different spaces. So that does explain why we've got left-handed and right-handed space. We have 2 spaces. That's what comes out of the mathematics. The commutation relations of these spaces, when taken together, the superposition of the commutation relations are SL31, the Lorentz group, which is exactly what we find in our 4-dimensional space-time. We get a right-hand Lorentz group and a left-hand Lorentz group. If we take the superposition of the rotation matrices, we get that. Take an exponential of that and we get the sines and the cosines. So let me... Superposition of the left and right matrices, so we're forming superposition of both left and right, all 6 spaces. That's what we get, and we take the exponential and we get the rotations that we find in our 4-dimensional space-time. So these representations in superposition give us the Lorentz group, they give us the distance function, they give us the rotation matrices and the trig functions, everything we've got in our 4-dimensional space-time. What did we do? We took a set of 4-dimensional representation of a finite group. We formed the superpositions and we found it could accommodate 2-dimensional rotations. Can this 4-dimensional space accommodate 3-dimensional rotations? Well, this is the representation of the cyclic group of order 6, C6, the 3-dimensional representation. They're the 6 permutations written as sign permutation matrices. We multiply them all by a real number, we add them together, we get that, and that's our distance function, which we saw before. Now, if our 4-dimensional space-time could accommodate that distance function, we'd see 3-dimensional rotations in our 4-dimensional space-time. But it can't. You set one of the variables in our 4-dimensional space-time to 0, you do not get that. And so 3-dimensional rotations cannot be manifest in our 4-dimensional space-time. One of the consequences of that is that 3-dimensional curls cannot be manifest in our 4-dimensional space-time. The only ones that can be are 2-dimensional curls. And what we're going to do, we're going to differentiate these groups eventually. We're going to get some curls out, we're going to pick out the 2-dimensional ones, and that's your Fermion content of the universe plus gravity and classical electromagnetism. Let's try the next page. Now, what's rather remarkable about this, let's go through that a bit more. Suppose that, wrongly, supposing we'd have found a 4-dimensional gauge space, a 4-dimensional representation space that had this distance function. We see that by setting any one variable to 0, we'd get that distance function. So such a space that had this distance function could accommodate 4 3-dimensional rotations. That doesn't exist, but that's how it would work. Well, what we did with one finite group, we can do with another. We got the order 8 dihedral group, and we took its, and we formed a distance function. So what we're going to do, we're going to form a distance function with the 4 3-dimensional spaces, and we're just simply going to add them. And we get this distance function. Well, that doesn't correspond to any rotation. Two-dimensional rotations correspond to a distance function of x squared plus y squared or t squared minus z squared. Four-dimensional rotations have their own distance function. That is not the distance function of any space that's associated with any rotation. And so, you cannot rotate in that space. And so that space has no geometrical structure. How many finite groups have a superposition space that can accommodate any rotations? In other words, how many superposition spaces can you have geometrical structure? And the remarkable thing is only the order 8 dihedral group, the only one. Now, I have a proof of this by brute force calculation up to dimension 15, and from that you can see there's lots and lots of others that won't have it, but it's not quite complete. I don't have a complete analytic proof of that. There's an observational proof, you just look around you. It would be nice to have a proof for every single finite group. I can tell you it's certainly true up to 15 dimensions, and there's lots of spaces there. There are 225 15-dimensional spaces. But the only one that, I'm pretty damn sure this is correct, the only group that has a superposition space, a superposition of its representations that has geometrical structure is that order 4, order 8, four-dimensional representations of the dihedral group. Now, that's a remarkable coincidence. Just out of nothing more than the real numbers, we've found a space that exactly matches our four-dimensional universe. It's inside the real numbers. You can't get away from this. Well, not while ever using real numbers anyway. And I'm willing to bet that that is why we have a four-dimensional universe. It's the only one that's inside the real numbers. It's really a superposition of both left-handed space and right-handed space. Right, I'm thinking that I might invite questions and comments. Go on, Sid.
So I have two questions, and I'll keep it at two. So you're starting with the real numbers.
Yeah.
Do you think that the reason why you have handedness in these groups and algebras is because of the positive and negative side, positive real numbers and negative real numbers?
No.
In this, okay. And the second question is, what are you? Did you say you're defining a space as a permutation group?
Yeah, you get a set of permutations, and you use that particular permutation group to pick out terms of the exponential series. In the same way, like the group C2 picks every second term of the exponential series out, and it forms a cosh function and the shine function. Well, as well as using C2, we're using C3 and C10 and all the rest of them. So we're permuting the terms of the exponential series. These are giving us sets of trigonometric functions which fit into rotation matrices, and they give us a distance function as well. They're a bona fide geometric structure.
So by permuting the exponential...
All you're doing is you're just picking out terms from the exponential series.
And you get a space.
And you get a space. And you get, well, you get an infinite number of spaces. So you pick out every 97th term, and you can permute them according to the finite cyclic group C97, then you're going to get a 97-dimensional space. You probably get millions of them actually.
Any questions from Zoom? John?
You're on mute.
Yeah, I'm muted. That was great, everybody. Thanks for that. I've got a couple of comments and some questions as well. So maybe I'll. First comment. It's interesting that when quaternions came out, you were talking about quaternion splits. Both Hamilton and Maxwell worked in left-handed quaternions, and so do computer gamers. And there is actually a difference between the left-handed and right-handed systems that was first pointed out by Phil Butler. In that if you look at rotations of rotations, so you've got rotating systems which are themselves rotating, then those rotations follow one another for the left-handed system, but some of them go in different directions for the right-handed system. It might be fun to look at that and see if that also, and see that you see that as well. Now you're mentioning that you think that space is so that's a comment. And then a question. You're saying that we're looking at a superposition of left-handed and right-handed space in terms of the space that we actually live in. I know you said something about this, but could you expand on that, please, and say why you think that there's a pair of spaces and that you want both of them? Is that bound up with the way that you look at four-dimensionality here? I wasn't quite clear on that.
Yeah. Right, first of all, yeah, the question of left-handed and right-handed quaternions is something I don't understand properly. It does seem there is a difference between left-handed quaternions and right-handed quaternions. The difference seems to be that to the left-handed quaternions it can be written as a pair of complex numbers. And this is really what they call a spiner is. The physicists will call a spiner a pair of complex numbers. But you can actually write it as a quaternion. And what physicists often do, they start with a spiner and they quantitize it. When they quantitize it, they add commutation relations in to something that didn't have them, and they promote a couple of variables to operators. Well, what they're doing, they're turning a two-dimensional complex vector, a spiner, into a quaternion. You can do that with left-handed quaternions. I don't see how you do that with right-handed quaternions. I don't properly understand that.
No, Peter might know more about that. He might have
Is it anything to do with our universe being left-handed to us rather than right-handed?
The left-handedness comes out of the commutator. The commutator has got a minus sign in the middle. It's got AB minus BA. If you put it the other way, BA minus AB, it'll all be right-handed. It's obviously arbitrary.
But it's only one. You can only do it for one.
You can only do it one way. That's where the left-handedness comes from.
Well, I think that's right. I think that we are in a left-handed universe, and we have to be. And I think you're very close to being able to prove that with if we're sticking to real numbers and permutations of real numbers. I think that's really cool. So yes. I mean, I've said in looking at some of the things I've been looking at as well, I've been led to having to use the left-handed system rather than the right-handed system. And one of my students has written a program which does all of these permutations for both of them, and looks at all the possible combinations. If you I can put you in touch with them if you want to have something which will do all this stuff automatically.
Superposition spaces. Yeah, the idea is simply that you can fit spaces together. If you've got two four-dimensional spaces from the same finite group, you just sit together on top of each other just by adding. The reason I came to that is that's really the only way it seems to work. It works later on when we get to tomorrow's presentation. We'll do the Maxwell equations. Maxwell equations come out of the real numbers, but they come out by taking a superposition of the left hand. The Maxwell equations come out of the quaternions. We take a superposition of the left hand quaternion fields and the right hand quaternion fields, and we get the Maxwell equations. By adding them.
That's mean addition. Is that right?
Yeah, it's just addition. You just add in. You're getting matrices, and you're just adding 6 matrices together.
That's not a yeah, okay, good, that's a simple addition.
That's what I'm calling superposition.
Yeah, okay, right here. So yeah, okay, no. Yeah, it's wonderful that you're doing this in the maths. And, yeah, you're right, too many words for some things, aren't there?
Sometimes, yeah.
Yeah, that's true, yeah. Good, thanks very much, yeah, no, I enjoyed that.
Right, well, coming back to tomorrow we're going to get a bit further, we're going to get the Fermi content of the universe.
So who's got a question?
Just a small, maybe silly question. But you mentioned axiom systems earlier and not wanting to be in that, to look at it in an axiomatic way.
Yeah.
I'm just curious if you wanted to talk a little more about that.
Well, yeah, basically, around about 1870s, 1880s, a big debate among mathematicians throughout Europe as to how we should properly structure mathematics. It's got lots of different parts that all seem to be connected, but there is no clear understanding of how they were connected. One school of thought wanted, including Hilbert and David Hilbert and a few others, wanted to just write down a set of axioms and make logical deductions from those axioms. And the big question, could they prove that the axioms were consistent? David Hilbert hoped that they would be able to. In 1931, Gödel proved that they couldn't. And would the axioms be complete? Would it be the case that we could ask a question within the axiomatic system that is not answered by that axiomatic system? For example, if we ask what is the linear factorization of x squared plus 1, we have to invent the number I to factor that equation linearly. That's an axiom. We've invented a new axiom. The square root of number 1 is I, and added that onto axioms. Gödel proved it would never be complete in 31. The other idea was backed by people like Russell, and Russell's wanted to build it on pure logic. Russell and Friese and a few others start from nothing more than logic and get the whole of mathematics. And I don't have a good understanding of exactly what he did. I know it's about 600 pages long, his Principia when he does it. It took him 15 years. And he gets to 1 add 1 makes 2. I think he's got to the real numbers. Right? And so the idea was to build the whole of mathematics up from logic. He got there, he got to 1 and 1 makes 2. He says this will sometimes be useful, and that's about as far as he got. And I think after 15 years, I think I'd have given over as well. And it seems that what I've done, I've started from the real numbers where Russell left off. And inside the real numbers we've developed the whole of mathematics as Russell and Friese would have wanted them to develop. Meanwhile, the axiomatic system was just shot dead by Gödel and nobody's acknowledging it. You go to mathematics lectures today, group theory, the first thing you get is the 4 group axioms. Algebraic structures, the first thing you get is the 14 algebraic field axioms. Metric spaces, the 3 metric space axioms. And you ask, where do these come from? And the answer is some bloke made them up. And I'm sorry, where were blokes, because they were all blokes in them days. Women never get things wrong. And that's really where they came from. And it's not structured any differently from a fairy story. You have axioms in a fairy story. Dragons exist, beautiful maidens exist, princes exist, and as long as they're consistent, you've got a consistent fairy story. And so I'm all for rejecting the axiomatic system. What this does, what I'm doing here, rejects lots of stuff. It rejects Hilbert spaces, rejects Lie groups, Lie spaces, Moody algebras, lots and lots of mathematics is now seen as being not mathematics at all. Because the only thing that's mathematics is inside the real numbers. And that is the remarkable thing is that what's inside the real numbers it seems to be an exact match for our universe.
I wonder if Bertrand Russell did his own accounts. You know, if he couldn't get past 1 + 1 = 2, yeah.
Well, if you reject the axiomatic system, then what are the real numbers?
The real numbers are what we find around us, what we observe.
Well, that's
what
we
you're
impose
saying is
on
how
what
do you
we-
define them, aren't you?
I mean, you do not observe real numbers. Real numbers is a conceptual structure that you're imposing on the things that you see. Show me a real number.
Yeah, I see your view there, and it's not a foolish view. I would take the view that real numbers really exist. There really is 1 electron.
But show me a real number.
Electrons.
You mean real numbers, not integers?
Yes, real numbers. Yes.
But all right. Even if I grant that 1 electron is 1, so show me a real number that's not an integer.
Well, obviously I can't show you a concrete real number, can I?
So it's a conceptual structure that you're imposing on observation.
If the real numbers were nothing more than a conceptual structure, then there would have been no real numbers before we had human minds to conceive them. And I'm quite sure that dinosaurs and stars and planets and atoms were all
Well,
reacting.
there's nobody around to call them real numbers, no,
Yeah.
because it's a conceptual structure that we are putting. No one would have put that conceptual structure on what we see.
Well, I think I'm of the opinion, and his opinion, and yours is opinion, is that the real numbers really do have a kind of existence, and not a concrete one. But there's a difference between dropping 1 kilogram of concrete on your foot and 20 kilogram of concrete on your foot.
But that has nothing to do with real numbers.
I would thought.
I mean, you can describe it in terms of real numbers, but I could say the same thing about matrices and metric spaces. I could say everything that you're saying about real numbers, I could say about matrices and metric spaces. They're complex numbers, right?
You're losing me a little there.
But it's going to be a matter of debate for a long time, that. But where you start, where do you start with anything? Wherever you start, you've got to start somewhere. And I think that what Dennis is saying is he doesn't see any need for all these axioms.
Yeah.
Whereas we're used to using real numbers and know that they mean something to us. But when you put 14 down axioms, how do you know that they're correct?
Well, I mean, what I would say you're doing is you're just not examining what the basis for what you're doing, because you are actually, when you manipulate real numbers, you are actually using axioms.
Sure.
Like commutativity and associativity.
You can put it that way. I think what he's saying is that you can get things by basing it on real numbers rather than something else.
But the real numbers are based on
The point is that the number of axioms matters. Now, of course, you have axioms in real numbers. You have an axiom of multiplication, you have one of division. You do have these things. But you have to have a look at what those numbers mean in reality. Now, it is absolutely true. There was a set of numbers before. Some people have argued before that, for example, there's a famous saying that God gave natural numbers and everything else was an invention, and that's perfectly true. But that's not the point. The point here is that if you're developing mathematics by shoving axioms in here willy-nilly, then every axiom you come up with may create a new mathematics, but it does take you further from reality. The question is, what are the words that describe reality? Of course, one could have no words at all, or what a word means, or how a word is a concept, or why that concept of word means anything, and what it means in different languages, because it does. But that's an irrelevant discussion which doesn't get one anywhere. What Dennis is saying here is that one doesn't need to go to the extra axioms which are shoved into string theories or strips in order to get really quite a long way in terms of understanding, amongst other things, why space has to be four-dimensional. Now, space-time has to be four-dimensional, which obviously it is. The question is why. And it's interesting that the combinatorics of that can be taken down to the mathematics of not just real numbers, but here real numbers that are in a matrix. So of course there are axioms there, the axiom of multiplication, the axiom of what he's calling superposition in terms of addition. These are things too. But you know, addition worked for humans. One sheep plus one sheep gives you two sheeps. So that kind of thing is there before humans and is not a human invention. People may be able to do that, but it's crazy. So it's not made up by humans. We know that this stuff's made up by humans. But the point here is that there is less than one puts in current physics by a lot in terms of the axiomatic nature that hasn't been used.
And it's also what you can get out. If you can get out something that's particularly interesting from a physics point of view, then that's the thing to do. And then people can argue about the axioms later, but I think that's what the idea of this presentation is.
Well,
yeah, I think
what
if you can
what
get
new
it
axioms are being introduced by string theory? What new axiom?
Well,
what you start with a very complex object as the basic.
That's not an axiom.
Yes, it is. You just made it up and shoved it in.
Well, I mean, what you're doing is you're choosing some kind of mathematical object to describe reality, but that's not a new axiom. You're still doing, in fact, all of the manipulations that were done here using real numbers, they do the same thing. There's no difference.
What they do in string theory is they stick in, first of all, there's quite a large number of axioms. You put in S. You start with a whole set of symmetries. You start with U1 plus SU2 plus...
That's not an axiom.
Yes, it is.
No, it's a model. It's not an axiom.
well, can we say that the proof is what you get out? What you get out of string theory compared to what you get out of something like this presentation?
Well, I don't see any difference between string theory and what Dennis has been talking about.
Yeah,
Dennis is saying these mathematical structures are associated with reality in this way. String theory says the same thing. In fact, you can express all of string theory in terms of real numbers
Well,
and
what do
matrices
they
and
get
things
out
like
of
that.
it?
Predictions.
Well, which predictions have turned out to be true?
No, that's true. But which predictions that turn out to be
Well,
true?
we'll find out in the next talk.
Well,
Isn't it a question
He's
about
not given
what's-
the next part of the talk, which is the physics part.
But I don't think you have any predictions that are not predicted by
I'm predicting the
conventional.
Fermi content of the universe, I'm predicting dark matter, I'm explaining neutrino oscillations.
So you're not predicting, you're explaining.
Yes, I'm offering an explanation. You can say it's a prediction it's in the mathematics if you want.
If he gets a number, it's a prediction.
So
If he gets a number for the fermions, or if he gets a number, that would be a prediction.
Well, we get the number of the fermions coming out. We get 4 forces for the quarks.
well, you don't get the number of fermions, do you?
Yeah.
How many fermions in the
We get
universe?
an electron,
Oh, how
neutrino.
many types of fermions?
Yeah,
Number of
type.
types of fermions.
Yeah,
Okay.
yeah.
I see.
Isn't it the question of like what is your starting point? Like what is the best starting point which gives you the most results?
But the thing is, he's always to look in a different direction and find out something which tells you something. And you don't have to necessarily prove everything else wrong. You just say, I've got this out of what I've started with. And that's interesting because this is telling me something about the universe.
Yes.
That's my argument.
Yeah, basically what we're going to do tomorrow is we're going to dig out all the two-dimensional curls. We're going to separate them out from the three-dimensional curls and the 5 and the 10s. And the set of two-dimensional curls is an exact match for the forces of our universe. Simple as that. It's the only ones that can be manifest in our space-time, because our space-time accepts only two-dimensional rotations.
So I did have a question about that. You have spatial rotations, and you have rotations that rotate space into time, right?
So the space-time
You had one with
velocity.
sine and cosine and one with sinh and cosh.
The sinh and cosh is...
Suppose you follow one by the other, what do you get?
you get the Lorentz group. What you can do is you can... Let's see if I remember this right now. You take two boosts and you get a spatial rotation in the Lorentz group. And
No,
that's
two
actually
boosts is
within
another boost, if they're in the same direction.
That's what you think, but in actual fact, when you get into it, you get a spatial
It's the
rotation.
same as you can get a rotation, it's analogous how you get a rotation from two reflections in the plane. You can think of a boost as a kind of a reflection in the
No, boost means that you're moving at a certain velocity in a certain direction relative to another person.
Yeah.
Now, if I do one boost and followed by another boost, then I'm just moving what velocity.
Sorry, I explained it wrong. It's one boost in that direction, followed by one boost
Right.
in the other direction. Yeah.
But that's not a pure rotation. That's not going to be a pure rotation.
From a mathematical point of view, change of velocity through Cauchy shine is pure rotation.
Well, you were distinguishing spatial rotation
Two types of rotation,
and yes, okay. But so my question is, and I think it's still a valid question, if you follow one type of rotation by another type of rotation, what do you get?
Spatial rotation followed by a boost.
Yes.
You can combine any set of these things, and what you end up in a general Lorentz rotation is both given by a rotation and a boost. If you add
That's
those-
true, but then you can't really say there are two types of rotations, because there's also the result that you get when you follow one type by the other.
Yes.
You can say it's generated by two types of
Yes, you
rotation.
can, because in a four-dimensional system you have 6 planes, and each one of those planes you can have a rotation of those planes. There are 3 planes which are space-time planes, and there are 3 planes which are space-space planes. And exactly as Dennis said, the space-space rotations have the form of a magnetic field, and the space-time the form of an electric field, the form of a boost and the form of a rotation. Absolutely you can. If you have a 4-dimensional system, it commutes to 6 and 2 indices, obviously. Because you have x2 for zt, xy, z, and zx, 6, exactly.
Well, you have a lot more than 6 planes.
There you go. In core D,
Only if you set one coordinate system. I mean, one plane, a lot more than 6 planes. I can just draw several planes in the...
that's absolute nonsense.
Well, we're just talking different...
I think we
guess we're
should
talking about each other.
call the discussion to a close now, and people can continue it over the lunch break. And I want to give applause for a really great presentation. Thank you.
Tactful.
What I want to do now is to put forward the idea that on Wednesday, if people want, we can have some sort of excursion. Where do you want to go?